And I guess a good question for both of you is, do you think there ever was life on Mars?
Elliot, would you like to take that?
Oh, so kind.
You're listening to The Cosmic Cast. Hello and welcome to another episode of The Cosmic Cast. I'm joined here with my regular companions, Ricky Bahir and
Hello.
Thomas Harvey.
You right?
And this week we've got two very special guests. We've got Elliot Sefton-Nash from the European Space Agency.
Hi.
And Manish Patel from the Open University.
Hello.
You're both really involved in a lot of missions, and specifically Exomars. How did you get involved, and what's the sort of things that sort of excites you about being involved with space missions?
I guess this is, for me, it's Manish here, by the way. For me, this is something I've been always interested in since I was very young. First started with astronomy, and my dad having a telescope, that kind of stuff, but then I must admit, I fell into this career quite accidentally. I didn't intend to do it. I always wanted to study space science. I did a degree course in it when I was at university, but then I got the opportunity to work on a space mission as part of a PhD, which I had not planned to do, but it was basically better than getting a job at the time, a real job at the time.
Yeah.
So I started working on the Beagle 2 mission to Mars.
Cool.
And that just opened my eyes to a world of possibilities there.
So you've always been at the Open University then?
I started at Kent, the University of Kent at Canterbury. It was one of the only places at the time doing a course in physics with space science and engineering, with a year of studying in the US as well. So it was my one choice to go there and do what I wanted to do.
It's been quite interesting working with Beagle then.
Yeah, it was a once-in-a-lifetime opportunity because a PhD lasts 3 years, and Beagle 2 was designed, developed, built, and launched in 3 years. So I had this really unique chance to come up with an idea for an instrument, design it, make it with my own bare hands, my bare incompetent hands at the time. But I learned a lot about how to do things in a very short time, and actually send it off all in one go, which normally takes, a decade at least in space missions. But this was a unique opportunity to get all of that all done in 3 years, and it was a big learning experience and basically set me on the career path I'm on now.
And Elliot, did you have a similar type of trajectory? Were you always planning to become someone who's working in research and space science, or?
Yeah, I mean, that's a nice image to think about. There are people who are astronauts who are like, well, I'm definitely going to be an astronaut. Yeah. And that's a nice, heartwarming story that they just pursued it.
There's got to be a level of confidence you have there to think, that's what I'm going to do, and then end up doing it.
I can assure you that's not me. Yeah. So in a similar way, actually, I suppose I kind of fell into planetary science as well. So, I was always interested in space, so I'd get out library books, like all the big, cosmology books and pictures of galaxies and things like that. And then I applied to do degrees in astronomy, maths and planetary science, and actually my first choice wasn't planetary science, but I didn't get into the astronomy one, so so I ended up doing planetary science, but it turned out it was actually probably ended up being the best choice.
I was going to say, it's clearly held you back in your career, hasn't it?
Obviously I could have been something. I kind of did my degree at the time when there was this wealth of data that people were analysing, returned mostly from Mars missions, from the cheap, fast Mars missions that NASA have been doing, Mars Global Surveyor, and in the wake of the Pathfinder rover, Sojourner, and then the Mars exploration rovers towards the end of my degree, touched down and started producing these amazing science results. So that was kind of a segue into doing a PhD in planetary science, and that ended up being mostly focused on remote sensing. So there were just terabytes of data, which at the time were huge, that were just, ripe for all of these kind of geologic studies that I ended up pursuing. And then after that, I kind of just over time developed better understanding of, this is what research is. I just found out something really interesting. I could do this. So I guess that's how I ended up here.
Yeah, because on that subject of if you ever seem to research anything to do with Mars or the moon, I guess maybe, I'm not sure, I'm not fully in the circle of lunar science anymore, I used to be, but anything you do kind of advances that field in Martian science at least. So it always feels exciting to know that you're learning something new about a planet that potentially we may eventually go to as humans as well.
Yeah, so contributing to something new is, always exciting. And there's often the realization that, this is quite an important thing. I should probably do it right and put some effort. And, maybe this is the first time somebody's discovered this. And that is very exciting. But it also leads to this problem of imposter syndrome, especially in academia, which is everywhere. But, on the other hand, imposter syndrome really prepared me for this job because I'm have experienced being completely out of my depth, but completely desensitized to it. So you just kind of get on with it.
So you eventually do get to a stage where you think what you're doing is the right thing to do.
Well, or that you don't really know, but you're just kind of going on empirical evidence. You're like, well, nobody seems to be complaining. I did the best I could, even though I don't think I know what I was doing.
I guess it comes to a point where you just got to sort of trust your own judgment, really, I suppose.
Well, yeah, especially for Manish, if you were involved in actually building parts of a robot that's going to go to another planet, there's a lot on the line there. So you must have to be really confident in what you're doing, and that's the right thing to do.
Yeah, it comes from a long time of listening to people. And, when you first start something like that, you have no idea how to solder a circuit board, how to cut parts in the right way so that they don't then fall apart later on. But you talk to people, you ask people how to do something, and you learn that process through, and you do it again, and you do it again, and suddenly you realize people are asking you. And, it's kind of, I think for me, it's certainly something that crept up on me, transitioning from working as part of a team into leading a team, and suddenly you're in that position. And that was a pleasant surprise the other day. Well, not the other day, but just recently, when you suddenly realize, actually, oh crap, people are asking me for advice when I used to do that myself. And it's a nice feeling, but it is a shock, and it is a bit of a scare when you suddenly realize, oh yeah, there's a lot riding on what I say and do and choose. And it's an interesting position to be in.
Well, remember, if you ever need advice, I'm only an email away.
I shall remember that.
So you made the Nomad instrument for the Exomars Trace Gas Orbiter.
Yep.
And just for the people listening, can you give a synopsis of what the instrument's used for?
So it's a spectrometer, so it looks at light coming from the sun and reflected off the planet, and we use that light to understand what gas molecules are present in the atmosphere, so we can...
Yeah, in the atmosphere of Mars. Yeah.
In the atmosphere of Mars, yes. Sorry. So this instrument is orbiting around Mars right now, taking data continuously, trying to understand all the tiny constituents of the Martian atmosphere to hopefully understand about the processes going on in the atmosphere at the surface, below the subsurface.
And how many years did it take you to actually develop it, and then before it actually was sent off then?
That was a long time. Actually, this stems back to Beagle 2, and it's kind of the evolution of the instrument I built there. So this is the big brother, the big sister, the next step. So we made it bigger and better, and able to go on an orbiter rather than on the surface. So the whole thing's been a career. It's a good, oh my God, 19 years. Now that's scary to think of. Don't ask me questions like that. But the actual process for Nomad was about a decade. We had 10 years ago with this opportunity to propose something. So we went into that point and then continued to today, where it's around Mars.
So that must have been a very satisfying moment when that first trickle of data started pouring in.
Yeah, I have 2 kids now, aged 4 and 3, but my firstborn child is that damn instrument. I spent so much of my life making it, building it, and then you literally deliver an instrument to the space agency. Even the terminology is the same. Yeah, so when you spend so much of your time and your life and your literally your life for the last 10 years, you put into something like that, and you see it go up, and you get that first data back, there's a massive relief, and then there's this a feeling of pride that comes along. It's like, yeah, actually it worked, thank God. I don't have to explain why that didn't work. No, it's a lot of effort and a lot of hard work, but it's worth it in the end for moments like that.
Yeah. So what sort of timescale has the Trace Gas Orbiter got around Mars? How long do you expect to get meaningful data out of it?
The Trace Gas Orbiter, it started a year ago, and we hope to get we plan to get 1 Martian year out of it, baseline, and that's 2 Earth years. But we hope that it will go on for a lot longer than that. If you look at something like the Opportunity rover that was designed for 90 days.
So is that funding dependent then?
Absolutely. Our funding dependent, the European Space Agency funding dependent enough to keep running the whole spacecraft and having enough fuel on board. But luckily we've got plenty of that. So I hope there's several years of science to come from that.
What are some of the main differences when you're thinking about building an instrument for an orbiter versus something on the ground like a rover or like the Beagle 2?
Yeah, it's a good question because they are very different situations to be in. Orbiters run continuously, they don't give up, so you have to design an instrument that can look continually and operate continually. So, and it's got to be much more flexible because you're looking at an entire planet. So you have to design more broadly for an orbiting instrument, and when you're on the surface you have a much more kind of focused, more specified operation. So you have to design things with much tighter constraints and much more optimization, if you like.
Elliot, your main focus is on another ESA project, the Exomars Rover, which is obviously attached to the Trace Gas Orbiter. And how did you get involved in that?
Yeah, well, it's interesting. So, I mean, it's as interesting as you think it is. But so Exomars 2020 is the rover mission, and 2016 is the Trace Gas Orbiter mission. So the rover mission is arguably the reason that I joined ESA in the first place. I was involved in some of the landing site analysis before I moved to ESA, and I helped run some of the workshops and do some of the internal stuff once I arrived. Although since then I've been kind of moved into a few different areas, but I'm hoping to get back into it as the preparation for science operations begin. This year and next, approaching launch in 2020. So, yeah, I mean, it's what better question to try and answer than is there life anywhere but Earth?
And that's the overlap, isn't it, really, between the orbiter and the rover. There's both interest there of whether there is life on Mars. And I guess a good question for both of you is, do you think there ever was life on Mars?
Elliot, would you like to take that?
So kind. So professional. Well, the conditions on Mars were once very, what we understand for Earth life to be habitable.
So we're talking about 3.7 billion years ago?
Something like that. Yeah. The Noachian period was 3.7 to 4.1. And arguably there was, either long continuous periods or short punctuated periods where conditions on the surface could have been quite hospitable.
So this is water, temperature as
water,
well?
Possibly temperature, pH as well was probably a bit more neutral than it was today. And this is evidenced by all the clay minerals that we see on the surface from spectra from other instruments. There's a lot of evidence for flowing water in the geomorphology that we can see from images. There's a whole bunch of good reasons why we should really investigate a few very interesting places for evidence that there could have been some past biology. Even if it doesn't resemble what we understand to be full-blown life, we can at least put some constraints on, how far does biology get in those types of conditions.
Exactly. There's so many pointers to environments suitable for life. For me, I always think about this question in the opposite way of, why shouldn't there have been life there? And our understanding of Mars now is that it was warm and it was wet. There was a nice atmosphere. There's plenty of water at the surface. To think that we are the only place in this whole universe that life could have arisen is, I don't know. To me, that seems a little bit egocentric. I think there probably will have been life in the past, but I don't think there's life on Mars now. I think that's pretty clear. But I think we're going to find traces of it maybe in the past, ancient fossilized remains, hopefully. The question for me is always, is there a reason it shouldn't be? And I can't really see one.
Yeah, more and more boxes are being ticked to say, there seems like there could have definitely been life back then. So I guess that's really a reason why we need to send something to the surface as well to look in an area and determine whether there could have been life. So once the ExoMars rover gets there, how will it actually look for life?
So the ExoMars rover, the key part that enables us to really sample the rocks that would be of interest is the drill. So we go to the subsurface where places that could have preserved evidence for past life, may have been preserved in the subsurface. So And the reason is that at the surface there's some pretty nasty, factors to deal with, like ultraviolet radiation, the very oxidizing chemistry that goes on that breaks down organic molecules, the galactic cosmic rays from elsewhere in the universe that continually bombard the surface. Below about 1.5 meters or so, there's not so many of those. So you want to look at places where you sample below that degradation horizon to get to the places where those types of molecules or that type of chemistry might have been preserved.
So would the drill actually be able to go lower than 1.5 meters then?
Down to 2. Yeah.
2, wow, okay, so yeah. The number we need, really. If the drill's only 50 centimeters, well, it's all we could afford.
But you don't have to go very deep to get below the oxidizing chemistry and the ultraviolet bombardment.
So how does that compare to other drilling missions around the solar system? Is that going to be a record-breaking drill?
So the Americans have done very, 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 very shallow drills into the rocks using a drill on an arm. But that's that's scratching the surface. This is going down way, or an order of magnitude in terms of more depth. It will certainly be a first, and it's a massive challenge.
Yeah, you must have to really worry when you've got a rover as well, so something that needs to be able to move around, and worry about where you're drilling just in case you get stuck, I imagine. There must be some protocol in place for it to remove the drill bit, or...
WD-40 maybe?
Maybe that's the case.
Oh yeah, there's a big canister of that. No, there's not.
It doesn't contaminate the samples at all when you put the WD-40.
Oh no, you're right. We should have thought about this. There are procedures for what happens in all manner of conditions when drilling, and that's something that the science operations team will have to, make decisions based on what is encountered. This is indeed part of the planning process that I think is ramping up now. What happens if you encounter something you can't drill through, but you're only at 20 centimeters? What does that mean? Is it interesting? Should you back up and go somewhere else? If it's a big flat rock, how big and flat does it have to be before how far do you have to go to try and avoid it? So there's all these kinds of things that you should consider. The drill is pretty capable. I think it can get through most stuff that we expect to encounter.
But let's say we look around and we find somewhere where we think is interesting to drill. So we get over to this point. Is it a drill arm that you can just stick out in front of you and look through a camera and go, okay, that's where we're going to drill? Or is it more complicated than that?
To try and paint a picture, it's a kind of multi-rod drill that's all assembled together in a horizontal box along the front of the rover, and the whole box tilts vertically when you want to drill.
So you're going to be drilling straight down. It's got to be straight down drilling, okay. And how do you see, because obviously you can't look below the rover, how do you see exactly where you're going to be drilling?
So you can. There are cameras that image the drilling site.
Right. Okay. Well, yeah, that makes sense.
There's actually a spectrometer in the end of the drill tip, so you get infrared spectra as you go down to understand the mineralogy.
Wow, that's cool.
You encounter.
That's really cool.
One thing you do before in the whole science context is achieved by the cameras. The panoramic cameras on the rover, so that will image the whole area. It will create this local area model of the whole area, so you effectively know exactly where everything is, and then you can compute where exactly to place the rover to get the drill in the right place, and then you have the cameras underneath, which you can then see what you're doing. But
so last Christmas, I didn't give you my heart, but
that's true. I didn't receive it. I was deeply offended.
Oh, so it's lost in the post somewhere. That's all
fair
right.
enough.
And I was at a Christmas meal with my family, and none of them are involved in academia in any way. And my uncle asked me a question, and it's probably the hardest question I've ever had asked to me. Why Mars, and why do we need to send people there? And why is that of any interest whatsoever? He asked in a much more aggressive manner than I have asked her, but it was along those lines. Yeah.
Was it kind of like, what's the point?
Essentially, it was those words exactly. Yeah. But so yeah, why is it of interest for us to send people in the future to Mars?
That is an interesting debate that we actually have in the scientific community ourselves, because there's this tension in our community of robotic exploration versus human exploration. And for a long time, the view in the UK at least has been we can do science, a lot more science. We can do the science we need to do with robotic exploration. I guess it's been fascinating in the last five or so years, the turn towards human exploration here in the UK. Suddenly we've got an astronaut. Suddenly we're yeah, let's send people into space. And the interesting thing is the inspiration side of it. You can do more science with a human present, in terms of you can do things a bit more intuitively. But I'm not convinced you can actually do more science. Absolutely, you send a robot up and they can work all night. They don't need to stop. There's energy, but astronauts have to sleep. So there's a balance between the two, and it's a very interesting question in that it's one that I'm looking at right now with another study for ESA, looking at the benefits of space exploration. What are the benefits? There's financial benefits. They are huge. But more importantly, I think there are social benefits. You're inspiring a whole new movement of people who are going to go into the space industry. You inspire people to work in STEM subjects, take on jobs, not necessarily work in the space industry, but learn skills that are then transferred into other elements of the economy. And there's every public talk I give, there's always a question at the end of, well, how much does that cost? Why don't we just spend that on feeding the poor? And it's a very good question. But the thing people don't see is that, well, we spend £1 on this mission, and it brings in, it generates £2 or £3 for the economy in the overall, in the ripple effects of what happens beyond there. So actually spending this money helps society in a very wide way. And sending people into space just rockets the inspiration side of it for the public. That's something we've seen. So humans in space is an inspiration, and we see what happened with Tim Peake in the UK, and it's a huge effect. Yeah.
So from that point of view, I guess following on from that, what do you feel about the Elon Musks of this world encouraging colonization and some of the other oddball ideas out there?
Well, it's having that kind of thing as a vision, a far future vision, is a great motivator. Mm-hmm. I think a lot of really long-term programs have to have something at the end that is pretty loosely defined at the start. Mm-hmm. And Elon's pretty good at pitching those to the public. And a lot of people have been really enthralled by that type of vision. I think space exploration is really hard, and humans are quite demanding. We need these little bubbles of atmosphere and nutrition and all this stuff, and it's quite difficult to take that to other places and keep us happy. But robotic exploration also has constraints. I mean, unless you're nuclear powered, you need sunlight to do operations. There's a limitation to the force you can apply to something. There's a limitation in the dexterity or the visibility. So astronauts are fundamentally, really, really useful to have in space. And you can argue in either way that an astronaut is more useful for this or a robot is more useful for that. In the end, if we can afford to, we would probably send astronauts everywhere we could.
The Elon Musks of this world are they're crazy, and they do these kind of things. Yeah, and it's like, well, that's just ridiculous. I love it. I think it's fantastic. I think you need people on the right side of the nut house line for that one, because it changes the landscape. Having that kind of commercial activity in space exploration has changed the entire landscape. Yeah. We've been talking about sending people to Mars for the last 20, 30 years, and it's always 20 years away. But now, with commercial exploration of space, it's actually suddenly accelerating into a reality, and it's accelerating in a way that hasn't happened before. And I really do think commercial applications of space has opened it up. Mm-hmm. In a way that is going to change things a lot. So
I guess it helps keep things in the public consciousness and keeps things at the forefront of their minds.
Yeah. Exactly. People now openly talk about going to Mars, and it's like, well, that wasn't the case.
Even 10 years ago, I guess, really. Yeah.
Exactly.
I was on the plane this morning here from the Netherlands to the UK, and there were two girls sitting next to me, and one of them said to the other, I've always wanted to be an astronaut. And I was like, right, here's my chance to do my public duty and say, you can be an astronaut. We have an astronaut program. You should check it out.
Did you have a leaflet with you?
Unfortunately, no. I left those at home, but I did the best I could.
Well, thank you both very much. I think we're just going to have one more question, something that we try to ask all the guests. So is there a particular sort of bit of science that are outside your respective fields that you find particularly exciting?
CRISPR movement and genetic engineering, that's a side. I've got nothing. I have no knowledge on that whatsoever. But that whole that's the Elon Musk for me. That's changed everything in a scarily fast way of allowing people to edit genes in the in their shed at home. It's
something that seemed like sci-fi a few years ago.
Still does, arguably.
Yeah, and it's crazy what that's going to enable, I think, in the very near future.
I don't think I can top that. I mean, my answer is not so far outside my field, but I was going to say exoplanets. Because the last couple of decades, there's just been this explosion in discovery of exoplanets, and we're on the cusp now of finding many, many Earth-like exoplanets. I mean, this is a fundamental constraint of the Drake equation, which historically has put a lot of doubt over whether we're alone in the universe or not. So I think this is a really blooming field that we can expect to see a lot from in the next few years. It will kind of change our outlook on the rest of the galaxy, I think.
Especially if that ties in with us finding life on Mars, and then we have all these exoplanets
Indeed.
that look similar to ours, then
Why not?
the game is entirely changed. Well, I think we should say once again, thank you very much to both of you come on, Elliot and Manish. You've both been great guests.
Thank you.
Thank you.